let's recap again the central point of this. We can directly alkylate the alpha position of a ketone using a base catalyzed enolization step followed by an alkylation step. And that gives us product, but it gives us poor yield. So instead, we start off with a beta-ketoester, and we still have the same first two steps. There's an enolization step and an alkylation step, but then in order to clip off the ester portion, we have a saponification step followed by a decarboxylation step. And I've color-coded these to try to help you see how each of these four steps will get you to a different point in your synthesis. And I've given you a lot of examples, and some of them are from different molecules, so let's bring them together and show you the full mechanism for this reaction process for just a single compound. It is color-coded to help you see where one step stops and the next step begins. So here in the black we have the enolization step, where our beta-ketoester gets deprotonated by ethoxide to form the enolate, and then the blue begins the alkylation step. The enolate unloads through the alpha position, pushes into the alkyl group, and bounces off the iodide. Then the saponification step. Hydroxide is added directly to your reaction. It attacks the ester carbonyl to form the tetrahedral intermediate, which then collapses down and pushes off your ethoxide. We'd like to be able to stop here, but we can't because the solution is basic. So once we make the carboxylic acid, then we have to take the hydrogen off to get the carboxylate. To put the hydrogen back on again, we do an acidic workup step. We get our carboxylic acid back, but then we heat it up, and this is where we cook off the carbon dioxide in the decarboxylation step. There's the three arrows in a ring system that is common to a Diels-Alder. In this case, we're undoing the Diels-Alder-ish chemistry, so this is a retro Diels-Alder. And then we get to the enol. These last two steps are tautomerization. That's where you change from an enol to a ketone, and the electrons will drop down to pick up the hydrogen, and then a final deprotonation step to get to our product. This is the same product that we got by alkylating the ketone directly, only instead of getting the poor yield, we get the high yield. And that assumes that the skill of the person running the laboratory is fairly high, because as soon as you start doing more steps, then it does increase the chance for error in the laboratory. But generally speaking, these steps can be pretty easy, so you should be able to run through all four of them and get pretty high yield. This EASD process looks very similar, and here is an example of one where we have beta-ketoester. We add a base to enolize it, and then we add in the alkyl halide for the alkylation step. There's a saponification step, and then the acidic workup and the decarboxylation step. And if you were to start with this particular starting material, then these are what the ends of each of those steps would look like. Here's the enolate, the alkylated version, the saponified version, and the decarboxylated version. This right here represents about the simplest possible molecule that you could push through this process. And so the specific name of this compound is ethyl acetoacetic ester, and they often use this as an example, the ethyl acetoacetic ester synthesis, to illustrate these four steps that we've been talking about today. One other example of these four steps that produces a slightly different looking product is the Malonic ester synthesis. So in the ethyl acetoacetic ester synthesis, you end up adding a new R group to essentially acetone. In the malonic ester synthesis, you add a new R group to essentially acetic acid. So it depends on what your product is that you want. You can think about these two different reaction pathways that have the exact same mechanistic features. So in the malonic ester mechanism, there is the enolization step, and then the enolate unloads into the alkyl halide, and you end up with an alkyl substituted diester. Then we run through the saponification step, so hydroxide is actually going to plug into both of these esters, and then we do the acidic workup to get a dicarboxylic acid. This is a geminal dicarboxylic acid. And then you heat up the geminal dicarboxylic acid and you cook it off to get this carboxyenolate, which then tautomerizes to give you your full carboxylic acid. The only other real caveat that you can do is, instead of running the 4 steps, you can kind of pause in the middle and do a second round of alkylation. So instead of being EASD, it's EAEASD. So then sodium methoxide right here will enolyze this thing, and then we add the alkyl group. Now we re-enolyze this thing and put a second alkyl group on there. Then you have the saponification, the acidification, and the decarboxylation step. So we typically think of this as a single decarboxylation event. So in summary, today we've looked at how you can put alkyl groups next to a ketone or an aldehyde. Doing it directly gives you poor yield, but if instead you start off with a beta-keto ester, then you enolyze, you alkylate, you saponify, and you decarboxylate.